for many years, has a lot of experience on modeling of flow through capacitive deionization, and I'm sure we will have a very interesting talk. Matthew, the floor is yours.
Thanks so much, Yauke. Thanks so much for the kind introduction. Thanks, Chia-Hung. Thanks for the organizing committee for having me here. I really wish I could be there with everybody. Unfortunately, I could not make it to Taipei, but I'll have to come visit at a different time. So yeah, today, can everybody see my slides? I think, oh, good, I see them on the camera. Okay, great. So today I will talk about basically numerical modeling and experiments, but basically how I feel and how numerical modeling has helped us unlock some really interesting separations with capacitive deionization, and kind of the idea that to really unlock the types of separations that we think are possible, it's really hard to do things intuitively, and numerical modeling becomes a very important tool. So that'll be one of the themes here of this talk. Okay. So I'm sure everybody's seen many talks now talking about ion selectivity, which is really a key frontier in water purification technologies, and the idea being that the removal of harmful ions specifically, and not removing benign or beneficial ions for processes. And this comes about because typical technologies such as distillation, reverse osmosis, they're largely non-selective. So they can do water desalination very nicely, but if you're doing kind of wastewater treatment for agricultural purposes, or removing key molecules that you want to save from water, for example, valuable nutrients, then you can't use these technologies. So examples where selectivity is important is water for agriculture. We'll talk about that. Valuable compound recovery like lithium, and things like heavy metal cleanup, where you really want to target and remove certain species, but not everything else from the water. So I won't really introduce kind of the technology, but all the projects I'm going to talk about today, and really the stuff we focus on in my lab, is membraneless capacitive deionization with these porous carbon electrodes. So I'm sure everybody here knows about it, but we're talking about basically electrodes with two scales for pore size. We have the macropores, the kind of highways through the electrodes, and the micropores, which are kind of the parking garages where the double layers form and where we store the ions. And you can imagine that the micropores, these kind of 2 nanometer smaller pores, really play a gigantic role in selectivity, and kind of tuning the environment in the micropores really tunes the separations, and we'll talk about that aspect as well. So we'll only be talking about kind of membraneless CDI with porous carbon electrodes in this talk, in my talk. So, okay, so if we are looking at these porous carbon electrodes, what are types of selectivity mechanisms? What can we do with micropores to change the ions that they want to electroabsorb? And so, of course, we can talk about things like steric selectivity, meaning you can make a pore size a pore at just the right size so that it doesn't allow in sterically a larger ion versus a smaller ion. So you can do play that type of game with the micropores. Even if there are two different types of ions of different sizes and both can fit into the micropore, you can also select between the two. Basically, when you pack the micropore, you can have a selectivity for the smaller ion. The smaller ion is preferred to be stored. So they both fit, but still there's an ion size-based selectivity that can occur. Charge-based selectivity, capacitive deionization, is an electrostatic technology. So it prefers to store the more highly charged ion, the +2 over the +1, for example, at long times and at high voltages. Dynamic selectivity, we've seen this happen before, where basically at short times you'll store +1, but then at long times it'll ion exchange and you'll store the +2. So at different times in the charging process, you can have different selectivities and different separations. You can imagine that if you functionalize a surface, if you put chemical charge on the surface, you can change significantly kind of the ion population inside that micropore, which we'll talk about. And there's also pH effects that can affect selectivity. They can affect the surface charge and surface chemistry, and also can affect the species chemistry. If you're talking about weak acids, for example, we'll talk about that as well. So, this is just kind of a subset of ways that you can tune ion selectivity in micropores. And what I'm going to hope to impart today is that you can imagine that all these things are acting in concert, basically. You can't really separate between them. You'll always have ion size effects, charge effects, pH effects, and functionalization, for example. And in water, you typically have, maybe a dozen different ions, maybe, half a dozen competing ions, anions, for example, or cations. And you want to achieve, the exact right separation. Some ions you don't want to touch, others you want to remove maybe nearly completely, and others you may want to remove partially. So to design a CDI system for such a complex separation where there's so many multiple species and selectivity mechanisms, That's a very complex problem, and it's very hard to intuit how that CDI system looks. And that's where kind of numerical modeling comes in and fills that gap in terms of how do we design systems for specific separations. Okay, so what I'll do is go through just briefly kind of the model infrastructure. And so basically, this is kind of the description of the numerical model we use to apply to various separation problems. And so we have two scales of pore size. There's the macropores and the micropores. So when you model the macropores, you have equations like transport equations and electroneutrality, basically. So here we have our electroneutrality equation and a transport equation, which governs transport of ions through the macropore, where we talk about things like Nernst-Planck fluxes, diffusion, advection, electromigration of species under applied fields. And what we also do is plug in a charge balance equation to capture the fact that charge can sink into the micropores, basically either through ionic or chemical sources. So we also write a charge balance equation. We capture in the model things like pH, so we can throw in pH-dependent species like weak acids and see how they're affected by the CDI charging. And pH effects, we have to account for kind of water autolysis reaction. So this model accounts for transport of all the salt ion minerals and also for pH effects, captures pH dynamics. Of course, you do the micropore as well. So we count for chemical charge effects, acidic groups, basic groups, for example, that can act in pores, and basically capture the electrosorption or repulsion of ions from micropores with the Donnan approximation. So a typical kind of Donnan approximation that relates the micropore concentrations to the macropore concentrations through the Donnan potential. Okay, and we have to couple these two models together, the macropore and the micropore model, couple them together and build the full cell type of model. So we have a model framework that we can throw in any number of kind of salt species, weak acid species, for example, different charges, different sizes. And I'll start talking about a project on monovalent ion selectivity with porous carbons. And the idea here, the application is that we really target is production of water for irrigation. So for example, in Israel, 85% of the water that's flushed down the drain is recycled, which is far and away the highest proportion of water recycled in the world, which is a very nice innovation that we see kind of coming out of Israel. But the problems we see in Israel now are that the wastewater treatment plants, which treat this water, they don't desalinate. And so over time, you see an increasing salinization of the soil. So salts accumulate after recycling of water, and it becomes a problem for irrigation. So if you're talking about agriculture, you want to treat water for agricultural processes, one of the things you have to do often is remove sodium selectively. And the idea is that if you have a feed water, usually you want to reduce its ion conductivity, but you also want to reduce its salt absorption ratio, which is basically, or the sodium absorption ratio, sorry, the SAR, S-A-R, which is the ratio of sodium to basically mineral ions, calcium, and magnesium. And you want that to be low enough, basically, to allow for kind of the proper soil permeability and soil health. And so typically around lower than 7 is typically desired for irrigation. So you want to reduce the conductivity, but you want to do so by removing sodium ions and not calcium, magnesium. So you want to be monovalent cation selective. And so how can we do that kind of thing with porous carbon electrodes? So, it's not so easy to intuit how to do such a thing. And so we led this project with modeling. And basically the idea is, you first put the model together, and this on the right here is the model result, which predicts the separation factor versus a scaled time. Okay. And separation factor is sodium versus calcium. So if separation factor is 1, it means you're equally removing sodium and calcium if they're at equal feed concentrations. If it's above 1, you're sodium selective. If it's below 1, you're calcium selective. Okay. And the scale time is scaled by the diffusion time across an electrode, which basically scales the charging process. So the charging process is, getting close to ending at around 1 on the scale time axis. So what we see is that when we charge a cell with what we call pristine electrodes, so just basically unmodified electrodes, not functionalized, we have this short monovalent ion selective window, but it's very short. On a scale time axis, it goes to something like 0.1, meaning it's not very practical for separation. So it's very hard to do monovalent selective separations. And after a certain amount of time, as we know, the separation becomes divalent selective. But so the short window is not good enough. We can't do anything practical with it. So how can we improve this situation? How can we make monovalent selectivity for a practical amount of time to use the capacity of the electrode? So in the model, basically what we can do is throw in, okay, let's try to functionalize an electrode. Let's try to functionalize the cathode in this system, which is storing the cations, and basically see what happens. And what we saw was that if you did functionalize the cathode, so you do what we should show in this picture, you put on these negative charge functional groups at the negative electrode, you have this monovalent ion selective window, which is extended. So you see that you're monovalent selected, you're above 1 on the y-axis until basically halfway through the charging process. So now it becomes something practical. Okay, so the model is kind of showing us, hey, we can't do monovalent selective separations. You need to functionalize your electrode in this way. So we buy off the shelf kind of activated carbons with very large macropores and small micropores that you can't see in this SEM, but the fibers, the woven fibers of this carbon cloth are filled with kind of these micropores. We can build a flow-through electrode CDI cell, which we do in the lab, which is pictured over here. And we also need to functionalize the cathode in the picture. And what we want to do is charge the short times and functionalize the cathode. And what we chose is for the functionalization chemistry is sulfonic groups, because they're basically strong acid groups, which is nice. So they're pH insensitive. And we can do things like direct titrations of our carbon. So we sulfonate the carbon. We then do a direct titration of it to show that we can get the very negative chemical charges. Okay, so we can see here versus pH of the solution that after you sulfonate, so the pristine material that you get has a little bit of native charge, some carboxyl group, for example, which brings it to a negative charge state, especially at high pHs. But then after we do the sulfonation, the charge gets very negative. And this on the y-axis is the micropore chemical charge concentration in molar. So we see that we can get to basically like higher than 1 molar of chemical charge after sulfonation. So we have a very kind of chemically charged micropore with these sulfonic groups. And that's what we're going to use for this separation. And then we can run CDI experiments where we run at a very high, basically star with a little bit of calcium and a relatively lot of sodium. And we do this shorter charging cycles where we charge to the dimensionless time of 0.67 or 3-minute charging, 3-minute discharging. Okay. And we get some results where here we plot basically the output water quality. So the feed conductivity is this dashed horizontal line at the top. And this dashed vertical line is the feed SAR, which started about 20, so pretty high. And we have basically here the pristine cell, which is the filled markers, and the sulfonated cell, which is the open markers at various voltages. So the different marker shapes are different applied voltages from 0.4 volts to 1.2 volts. And what you can see is that for both of these cells, with the sulfonated electrode and the one without the sulfonated electrode, sometimes you charge the cell, and every time you charge it, you reduce the conductivity, you pull out ions. But sometimes you do so in a way that hurts water quality. So you pull out the wrong ions, meaning that the conductivity is reduced, but the SAR is increased. For example, we see that in these points over here, right? So you're not being monovalent selective, you're being divalent selective, and you're hurting your water quality, even though you're pulling out ionic species. But then as you go to higher voltages down here, we start to see that indeed we are now pulling out kind of more of the monovalent ions. We're reducing the SAR, which is the right direction, and that the sulfonated pristine can get to improved kind of water quality or the best water quality. So the sulfonation helped here in terms of getting to a better water quality and a more monovalent selective separation down to a SAR of about 16 and conductivity of about 1.1 millisievert per centimeter. The interesting thing is that, when you go to short charging times, what happens is that the coulombic efficiency becomes very high. So we had here like a 97% coulombic efficiency, and coulombic efficiency is a measure of the side reactions, and side reactions tend to hurt your electrode lifetime. For example, the oxidation of carbon is a side reaction that hurts its lifetime. So we thought, since we are short charging and we have high coulombic efficiency, maybe we can go to high cycle life. Like, let's see what the lifetime performance looks like. And here's a result basically of cycling this cell 1,000 times. Where we plot on this y-axis here, which is this purple line, versus the cycle number, the separation factor, okay, of sodium versus calcium. And you see at the first cycle, the separation factor is about 0.8. So we are almost equal in terms of calcium and sodium. And then what happens is it starts to increase in time, which is a very interesting phenomenon we found. So actually our separation is improving in time with cycle number, because as the cell ages, it actually becomes more monovalent selective, which was a really interesting thing that we found. And the coulombic efficiency remains at around 97% or so throughout this experiment. We do lose a little bit of capacity. In the inset, you see that the conductivity of the product water goes slightly up versus cycle number from about 1.1 to about 1.2 after 1,000 cycles. But we are increasing the sodium selectivity. So which is quite nice. Okay. So, in terms of this monovalent selective separations, what's coming this year, kind of what are we working on, and what do we think we're going to have out the door this year? Basically, what we did is we had a numerical model, and we went and did this kind of careful model versus experiment comparisons, because I showed you the numerical model predicted that functionalization helps. I didn't tell you why, what the mechanism is. Why does this functionalization help? And so we want to really understand deeply kind of what is the mechanism here. So that's the stuff that kind of we figured out, and basically we submitted for publication at the moment. And once we really understood the mechanism, we could go to yet stronger monovalent separations. So here's some data basically showing that more recently we've changed the chemistry of the electrode, we've changed a few things. The model is and the mechanism has kind of helped us understand how to improve this. And we can get to separations, as you see here, at this minus 0.6 volt discharge voltage, where we can store uniquely sodium ions and not store calcium ions. So we can really take this to the limit where we're only storing monovalent ions and not storing divalent ions. So really strong kind of monovalent selective separations. So basically these porous carbons, which are, with different surface chemistries, can help be monovalent selective for these agricultural separations. So now switching gears a little bit to a bit of a different project. We talk about monovalent ion selectivity, but there are other applications where you kind of want to do the opposite. You want to be divalent ion selective. Okay. And the idea is that, if you have these hardness ions, calcium, magnesium, sometimes you want to remove them preferentially to prevent scaling. For example, in an upstream process for brackish water desalination, for high water recovery desalination, you want to remove the calcium, magnesium so you don't scale the RO membrane, for example. Or just other processes where you worry about scaling pipes or tubes. So, the idea here was, what we know is that if you charge to short times, you're monovalent selective. That's what we did in the previous project. But if you keep it going for longer times, you eventually switch to divalent selectivity. So if you charge for very long times, you exchange ions and you become divalent selective. Okay. And so the idea is we had this sulfonated electrode. So the idea is that it's an electrostatic effect of divalent selectivity. So we have these negative charge surface groups in the negative electrically charged electrode. So we have a lot of negative charges there, chemical and electrical. And since it's very charged, we thought, maybe the divalent selectivity could be improved if we charge to long times now instead of short times. So basically, we ran a cell with 30 minutes full cycle time. So 15-minute charging instead of what we did before, 3 minutes. Now we're going to 15 minutes. With a feed of 3 millimolar calcium and 15 millimolar sodium, so it's type of brackish water, basically type of concentrations, with a sulfonated pristine cell. And what we found is that here we plot on the y-axis electrosorption, micromole per gram, versus the cell's discharge voltage. So the cell was always charged to 1.2 volts, but we varied the discharge voltage. And what we saw was that the calcium was stored very significantly, like basically, between 150 and 100 micromole per gram. But the sodium, especially as we got to these higher discharge voltages, really was not stored at all. So the idea was we were removing calcium, but not sodium, which is a really nice application or basically a nice concept, I think, because you're charging your CDI cell and you're removing uniquely the minority species, the calcium, which is 5 times less present than the sodium. So it can be so selective that it just reaches in the CDI cell and just pulls the minority species and doesn't pull out the majority species. And that's what we see at 0.2 volts and 0.4 volts discharge voltage. So, what we call this, when you define your separation factor, is the electrosorption basically of calcium versus sodium normalized by its feed concentration. We're not electrosorbing sodium at all. So the idea is that the separation factor here is going to infinity. So we call this a perfect kind of selectivity, where you just take one species and not the other species. And as you can see in the plot on the left, we have also theory lines that kind of predict the same phenomena that we see experimentally. So we kind of validate what the theory was showing as well, that, hey, we can do this perfect selectivity. And if you look at a kind of historical review, the idea here is on the y-axis, we have this kind of divalent separation factor, the calcium to sodium divalent selectivity. That pretty strong selectivity had been seen before, like a separation factor of 23 for calcium versus sodium. But, it hadn't been shown before with any type of electrode material that you could do perfect separation, as far as we were able to find in the literature. So it was interesting that you could do this kind of perfect separation, really just remove this calciums and not the sodiums. And, if we take a step back for a second, this kind of all goes to show that CDI can be very dynamically tunable, right? Because we talked about we had one cell for both these projects. The cell was one sulfonated cathode and a pristine anode, right? That was the cell that we used for monovalent selectivity and we used for divalent selectivity. And if you charge it to long times, you can be perfectly divalent selective. And if you charge it to short times, you can do this kind of long-lasting monovalent ion selectivity. And the only thing you're changing here really is just kind of user-operated parameters. You're changing the times, maybe you're changing the voltages, but it's the same cell. So you can imagine that this could be very kind of dynamically tunable, that just by changing parameters, an operator can switch the amount of selectivity that they get in the output water, which is important, as you kind of talk to industry, because a lot of times, especially in Israel, I don't know how it is in other countries, but industries that use water get different water quality every day, and they need to use it for their processes. And there's, tuning water dynamically to kind of changing inputs or even changing processes is an important kind of demand. So CDI can fulfill that. Okay, so for the third project, I'll switch gears a bit, and I see I've got a few more minutes, so that's good. I'll try to end off by in about 8 minutes, so we can have a few minutes of questions. And this is the project that we did together with Jouke and Martin in the Netherlands on boron removal with kind of porous carbon electrodes. And maybe even Jouke talked about it already, so I might be repeating it, but repetition is good, so everybody will walk away knowing about this boron project. So the thing with boron is that it's a problem in seawater desalination by reverse osmosis. There's a pretty high level in seawater, 4.5 milligram per liter in seawater, and you want to get to under 1 milligram per liter. And in the Mediterranean, it gets to 9 milligram per milliliter. So even in the Mediterranean, it's even higher. And the thing is that, boric acid is a weak acid, basically, so that with a pK of about 9, just over 9. So when you're at neutral or near neutral pHs, basically it's the ion is the boric acid is not deprotonated. It's not charged. It's a small molecule, and it goes right through the reverse osmosis membrane. When you go to higher pHs, what happens is you dissociate. So you need to go to pH 9 or 10, and you dissociate the boric acid, and then the boron hydrates, becomes larger, and can be filtered out by RO membranes. So the fact that boric acid is neutrally charged at the seawater pH is a problem. It doesn't get filtered out well by the reverse osmosis membrane. And it becomes a big problem to kind of treat boron. It takes a lot of extra energy and sometimes chemicals to raise the pH. So the problem is, how do we get boron out of water? And the interesting thing of using CDI here is that CDI cells have these naturally arising pH gradients. Every time you charge your CDI cell, you get a very large pH gradient across your cell. And so these are measurements of another group out of Kentucky in the USA, where they measured the pH on the surfaces of these electrodes during charging, and they found that there's the anode pH goes down to close to 2, and the cathode up to 10. That's a gigantic pH gradient that forms just as you're charging your cell to do kind of your brackish water desalination. So these kind of pH gradients are naturally arising. And you can imagine a strategy where you say, okay, so we have these pH gradients in CDI cells, so how do we use that for boron removal? Well, you can imagine saying, well, if we have high pH at the anode, right? If we can get a high pH zone in our anode, that's perfect, because in that high pH zone, we can dissociate boric acid, and the B- ion can be stored at the anode. So we can do simultaneous dissociation and storage if we have a high pH zone in our anode. So how do we do that? So intuitively, you might say, well, look, the cathode has a high pH. So why don't we put the cathode upstream? We'll push that high pH into the anode, and we'll leave like a zone basically near the cathode side of the anode that's high pH at the anode, and we can desorb the boron or dissociate boron and electrosorb the boron anion. So that's intuitively what you think might happen. And a picture showing that intuitive thing is, so you flow through your system, you charge it, the cathode becomes high pH because the H pluses are electrosorbed in the cathode. The anode becomes low pH, and now you have a high pH zone in your cathode, and if you flow through it, you push that high pH zone into the anode. And that's where you can now in the anode simultaneously deprotonate boric acid and store the boron anion. But the problem is that doesn't work. That nice picture, that intuitive way of thinking about it is not what doesn't work in reality. And it was the model that told us this. So the model led here again. And basically the idea is that if you look at the model, and luckily we started with the modeling, because we had this model and it's a complicated process when you add in pH dynamics. So we started with the modeling, and the model told us kind of this result here, which is if we go with this intuitive design where the cathode is upstream, the flow direction is from left to right. And this result here is a spatio-temporal plot of pH. So X is the position in the cell. So cathode on the left, separator in the middle. This thin region is a separator, and then anode on the right. And then time is on the y-axis, and color is the pH. Okay, so we're looking at the evolution, the dynamics of pH in the cell as you charge. So what happens is that even though the flow is going from left to right, a low pH zone propagates against the flow from the anode to the cathode. So there's a very strong electromigration here, which actually means that the high pH zone in the cathode does not get into the anode. It goes against, even though that's the flow direction, the low pH zone from the anode goes upstream. And that wasn't what we expected, but that's what the model suggests. So, these pH dynamics that we plot here are quite complicated and really interesting dynamics. They're shock-like features. I can't say we understand all the features of the dynamics, but, the model again is telling us that this strategy won't work. Although we thought it would work intuitively, it's not going to work. But if we do the opposite, if we put the anode upstream instead of the cathode, so we just flip the direction or the order of the electrodes. If we put the anode upstream, now we see something that looks like it'll work. Now we see here a high pH zone in the anode. There's this thin region here in the anode, just next to the separator, which is a high pH zone in the anode. So that's the right conditions for storing boron anion, right? For dissociating and storing the boron anion. So that's what the model said. What did the experiments show? So if we plot basically electroabsorption of boron on the y-axis versus Peclet number, which is basically a measure of how fast we're flowing. And then the model predictions are this dashed line for the intuitive cathode anode configuration, which shows no electroabsorption. The model says the intuitive order doesn't work. And then some boron electroabsorption for the opposite electrode order of anode first and then cathode. And what did the experiments show? So the experiments for the anode cathode show that we did detect boron electroabsorption, but we did not detect it for the opposite configuration. So indeed, the counterintuitive kind of way of going about this is the one that worked and was able to let us remove boron like the model predicted. So again, the model played a very big role in kind of helping us understand how to design the cell for this type of separation. So, what's been more recent, this is kind of recently published this year, again, together with Yauke and led by kind of Amit Chokron, is basically saying, okay, now we know how to remove boron, but we didn't remove enough boron. We showed we could do it, but we wanted to remove more. And we were able to achieve an order of magnitude enhancement, again, leading with the model. So the idea is we explored the parameter space with the model, and we found that if we decrease the discharge voltage, it's an easy way to boost boron electroabsorption. And here are some results, basically. So on the left plot, you can see, again, boron electroabsorption on the y-axis and discharge voltage on the x-axis. And the previous results were for 0 volt discharge voltage, kind of the standard. But the model predicts, this solid line is the model, it predicts that if you go to lower discharge voltage, you'll increase boron electroabsorption. And the experiments also demonstrated that. So if you went down to minus 0.2 volts, you got basically kind of this huge enhancement in boron electroabsorption. Now, the model and experimental trends did not really follow each other so nicely. So there's some discrepancy between model and experiment, but the basic concept of reducing discharge voltage, getting higher boron electroabsorption was demonstrated in the model and the experiment. And that allows us to basically get enough boron in a single pass to just about get to the WHO kind of limits in a single pass. And you can imagine just a bit better cell engineering would remove more boron per pass, because now we're electroabsorbing enough, basically. So we're electroabsorbing enough boron to, in a single pass, feasibly treat kind of RO permeate. Okay, great. So I'll conclude now, and the idea is that, what I hope to demonstrate here is that these activated microporous carbons, the carbon electrodes that we kind of focus on here, they're pretty inexpensive scaled material that we buy off the shelf and we sometimes functionalize, which can perform really interesting separations for such kind of a widely available, inexpensive material. But, when it comes to these complicated separations, numerical models are crucial to really leading with numerical models oftentimes. And we needed that for several of our projects because of the complexity, how many ions you have, and the amount of mechanisms at play. So to really design your system, starting with numerical models is important. I gave 3 examples here of long-lasting monovalent selectivity type separations for irrigation applications, divalent selectivity for water softening type applications, and boron removal from RO, seawater, RO permeate, all of these activated porous carbons. The key last point to kind of leave you guys with is that, how practical is this technology? And the idea is that it could do really interesting separations, and the material is very inexpensive. All that's really nice. But lifetime is a key issue. So the key issue really is demonstrating longer lifetime. And what we've seen in my lab is that, lifetime can really be improved just by basically operating these things at lower voltages at shorter times. That can help a lot in terms of lifetime, but still there's a lot of work to be done in terms of showing that these things can last for years in these applications. So thanks very much for your attention. I'd just like to thank a bunch of funding agencies and of course the people in the lab who did the work that I showed here. So of course, there's Amit who did these numerical modeling, most of the numerical modeling, and also Zohar has been doing the more recent numerical modeling for the monovalent separations, but Amit did the boron modeling and the initial kind of monovalent selectivity modeling as well. Eric did the monovalent ion selective experiments, and Ankita has done the more recent version of those experiments, and Rana did the experiments for the divalent ion selectivity, and of course collaborators, of course, great collaboration with Jouke and Martin in the Netherlands, Charles Diesendruck, who is our collaborator at Technion, who basically is making these functionalized electrode materials or developing the protocol. So a chemist who's helping greatly with these projects, Charles, and also Manny Elimelech and Jack Gilron, who we collaborated with on this divalent selectivity project. Thanks very much for your attention, and happy to take any questions.
Thank you, Matthew, for this very interesting talk. I'm sure there are questions. Who has a question? I saw online, there's in the chat. So the first question, Matthew, perhaps you see the chat as well, but I will read the question. Is it possible to achieve this high selectivity by using a flow by cell rather than a flow through cell? Can you comment on this?
Yeah. So yeah, it depends on the separation. I mean, there's some interesting things about a flow through electrode cell, meaning like the pH differences inside the electrodes is kind of can be much stronger than what you get between the electrodes. So you can access kind of like more extreme pH variations if you're flowing the feed water through the electrode pore space. So if you have these kind of pH sensitive separations, like with weak acids, for example, you might want to try to understand what flow through electrode give you versus flow by, and there's possible there's some enhancement there. For the other separations like the divalent selectivity, I don't think it's so important, the flow configuration. We have a flow through electrode cell just because it's, you can get away with a more narrow kind of cell geometry with a thinner separator. But in terms of the specific selectivities, I'm not sure that'll be so much affected by the flow scheme, but we haven't tried it.
Thank you. Was there another question just above? Oh, okay. Are there any questions here? I have a question. I was wondering, you also touched this topic at the end of your presentation. So you have these electrodes with perfect divalent selectivity for cations, and you tested this on calcium. Does this also work for magnesium? And slightly related to that, can you comment on the stability of these materials for a longer period of time?
Yeah, absolutely. So yes, we've tried magnesium also, and magnesium behaves in a very similar way to calcium, and that's kind of what you might expect because they're the same charge, very, very similar sizes. But yeah, you get the same kind of strong separations with magnesium as you do with calcium. We've done some lifetime testing, and the lifetime testing was actually talked about in Rana's talk, which was maybe yesterday. I'm not too sure what the time zone shift, if it was yesterday or 2 days ago, but yeah. And so the idea with the cycle testing is actually was quite. So we did, I think, something modest like 25 cycles to now. And it did quite well. And mainly we were worried about scaling more than we were kind of electrodegradation. But still, it maintained after 25 cycles, like the capacity loss was quite small, which was great. So there's still a lot of cycles to kind of test that out. But so far so good on lifetime. Like we don't see a very fast degradation basically of the system at this point in time. There definitely to get to like 1,000 cycles or to operate for months at a time or so, there's going to need to be some serious study and some kind of optimization of parameters. But so far so good with lifetime.
Okay, thank you. Are there questions from the audience? Online, there's a question by Xiaowai Sun. With the anode in the upstream, is the pH, does the pH become higher in the anode or the other way, since boron is supposed to be absorbed in the anode?
Yeah, okay, so when the anode is upstream, yeah, I'll just quickly get back to those results here. We have these predictions. We, of course, didn't measure pH inside the electrode space. I wish we could do that, but we don't know how to do that. But so the best thing we have to understand the pH is these predictions, the model predictions. And what they predict is that the pH in the anode is, for most of the anode space, like the anode goes from 0 to 1 on this x-axis. And so for most of the anode space, the pH is below that of the feed. It gets acidic. But there's this small band right here where the pH goes up. It kind of comes in from the cathode, basically. So there's this upstream migration of this kind of high pH zone. But for most of the anode, the pH is quite low. I mean, you can see here, it's basically, between 5 and 6, basically, as you can see here. I hope that answers your question.
I think it does.
Okay.
Any last question? Thanks. I see. Well, then I suggest we move on, and I would like to thank you once more, Matthew.
Thanks very much.